This video is the third video in our ongoing tutorial series on CCNA. In this video, we will learn about the Unicast, broadcast, and address resolution protocol. We will use a simple network to understand these terms. In this network, we have 4 PCs. We have an Ethernet switch placed in the center of this network. It connects PCs using Ethernet cables. All PCs have the necessary network configuration to communicate in the network. A network configuration consists of many settings, including hardware and software addresses. We will learn about these settings in upcoming videos. For this video, we need to understand only hardware and software addresses. A hardware address is known as a MAC address. A software address is known as an IP address. A hardware address is part of the LAN card. All LAN cards have an inbuilt MAC address. We do not need to change or update this address. Software addresses require configuration. We have 3 methods to configure it: manual, DHCP, and automatic. In the manual method, we manually configure a software address on all devices in the network. In the DHCP method, we configure a DHCP server in the network. A DHCP server provides IP addresses for the network. In the automatic method, operating systems assign an IP address if the system fails to get an IP address from the manual and DHCP methods. This address allows the device to communicate with other devices on the local network. No matter how a device gets an IP address, it can communicate with other devices in the network only if it has it. For this tutorial, let us assume that the administrator manually configured all devices' IP addresses. Now, let us see how communication takes place in this network. Suppose PC1 wants to send a file to PC3. For this, PC1 needs to know the IP address and MAC address of PC3. PC1 can learn the IP address of PC3 in 2 ways. It can use the host's file or a DNS server. A host's file is a text file. Almost all operating systems have it. It allows us to map IP addresses to names. If this file does not contain an entry for a name, the system uses the DNS server to translate the name. A DNS server translates names into IP addresses in the network. You can check this video to learn more about the host's file and DNS server. It explains how the name resolution process works. For this video, let us assume that the administrator created entries in the host's file of all PCs. From the host's file entries, PC1 learns that PC3's IP address is 10.0.0.3/8. After knowing PC3's IP address, it needs to know the MAC address of PC3. It uses the ARP protocol to learn the MAC address of PC3. ARP protocol uses a simple mechanism to know the MAC address of the given IP address. It sends a broadcast message to the network, assuming the device with this IP address will listen and reply. The broadcast message includes the source's MAC address, IP address, request message, and intended device's IP address. The broadcast message reaches all devices in the network. A recipient device matches its IP address with the IP address listed in the indented IP address field of the broadcast message to determine whether this message is for it. This broadcast message is for the device with the IP address 10.0.0.3/8. PC2 and PC4 ignore this message as their IP addresses do not match with it. Only PC3 replies to this message as its IP address matches the IP address listed in the indented IP address field of the broadcast message. Since this message also includes the PC1's MAC and IP addresses, PC3 does not need a broadcast message to reply. It can send a direct message to PC1. A direct message is known as a unicast message. PC3 sends a unicast reply message to PC1. The reply message includes PC3's MAC address. PC1 learns the PC3's MAC address from the reply message. After learning PC3's MAC address, it sends the file directly to PC3 using a unicast message. Let us understand this process through a packet tracer example. Packet tracer is network simulator software. The second video of this series explains how to download and install it. Drag and drop 4 PCs to the workspace. These PCs simulate end devices in the network. Now, add a switch to the workspace. Connect these PCs to the switch. You can use the auto connection feature. It automatically creates the necessary connection between the devices. If you want to make a manual connection, use a copper straight-through cable. Assign manual IP configuration to simulate our example. We will learn more about IP addresses in upcoming videos. For now, you can use these IP addresses. As explained earlier, An end device needs both the MAC and IP addresses to communicate with other devices in the network. It gets the MAC address from the LAN card and the IP address from this configuration. Now, this lab is ready. By default, Packet Tracer works in the real-time mode. In this mode, it does not show how data flows in wires. Switch the default mode to simulation to visualize the data flow. By default, it tracks all protocols. First, remove all protocols. Then, add only ARP and ICMP to the tracking list. Now, open the desktop interface of PC1. Open the command prompt. The ARP command with the A option lists the current ARP entries. As we can see here, this system currently has no ARP entries. It means if it sends a data packet to any device, it has to learn the MAC address of that device first. The ping command can generate and send dummy data packets to any end device in the network. However, it sends data packets only when it knows the destination device's IP and MAC addresses. It requires the destination IP address as the argument. It uses the ARP cache to find the MAC address associated with the IP address. If the ARP cache does not have an entry for the specified IP address, it first uses the ARP protocol to find the MAC address. Let's see this event in simulation mode. Start the event tracking and send ping requests. The ping command generates a dummy data packet but does not find the destination device's MAC address in the ARP cache. It halts the data packet and generates an ARP broadcast message. The message reaches the switch. Since it is a broadcast message, it forwards it from all active ports. PC 2, 3, and 4 receive this message. Clicking this data packet shows its header entry. PC 2 and 4 ignore this message as their IP addresses do not match those listed in the target IP field. Only PC 3 accepts this message. In reply, it sends a Unicast message to PC 1. Since it is a Unicast message, the switch forwards it only from the port connected to PC 1. Let us compare its header with the header of the broadcast message sent by PC 1 earlier. It is the destination address field. A broadcast message always has this address in this field. It is a local broadcast address. It belongs to all devices in the network. A Unicast message contains the MAC address of a particular device. For example, this Unicast message has the MAC address of PC 1. PC 3 learned this address from the broadcast message it received from PC 1. It is the source MAC address field. It always contains the MAC address of the device that generates the message. For example, PC 3 generated this message, so it has the MAC address of PC 3. PC 1 generated this message, so it has the MAC address of PC 1. It is the source IP address field. Like the MAC address field, it always contains the device's IP address that generates the message. It is the IP of PC 1. It is the IP of PC 3. This field holds the MAC address of the intended device. In a Unicast message, the sending device knows the MAC address of the recipient. It uses the recipient's MAC address in this field. In a Unicast message, this field and the destination MAC address field have the same value. In a broadcast message, the sending device does not know the MAC address of the recipient. It uses a MAC address that represents all devices in the network. Like the destination MAC address field, this field always contains this address in an ARP broadcast message. This address is known as the Universal Network Address. Similar to the broadcast MAC address, it belongs to all network devices. This field holds the IP address of the intended device. In a Unicast message, it is the IP address of the destination computer. In an ARP broadcast message, it is the IP address of the device whose MAC address the sending device wants to know. From this message, PC 1 learns the MAC address of PC 3. The ping command attaches PC 3's MAC address to the dummy packet and sends it. The packet reaches PC 3. PC 3 replies to this packet. The reply message reaches PC 1. The ping command verifies the reply message. The ping command uses the MAC address stored in the ARP cache for the following data packet. ARP cache improves network performance by reducing the number of ARP broadcasts. Let's view the ARP cache entries again. As we can see, PC 3's MAC address is available in the ARP cache. PC 1 learned this address from the ARP broadcast it received from PC 3. This mechanism explains three things: broadcast, Unicast, and ARP protocol. Let us quickly summarize these things. A broadcast message is for all. It contains predefined IP and MAC addresses in the destination IP and MAC address fields. These IP and MAC addresses belong to all devices in the network. All devices listen to them. Devices use their logic to determine whether to reply. The sending device does not need to know the destination device's IP and MAC address. A unicast message is for a particular device. It contains the IP and MAC addresses of the intended device in the destination IP and MAC address fields. A device can send a unicast message only when it knows the IP and MAC addresses of the destination device. ARP stands for Address Resolution Protocol. End devices use it to find the MAC address associated with an IP address. It works in 3 steps. The source device sends an ARP broadcast to know the MAC address associated with an IP address. The broadcast message contains the source device's MAC and IP addresses in the source field, the intended IP address, and the broadcast IP and MAC addresses in the destination field. Since the broadcast message contains the IP and MAC addresses that belong to all devices listen to it. They compare the intended IP address with their IP address to determine whether it belongs to them. Only the device whose IP address matches the intended IP address replies to the message. All other devices ignore it. The matched device sends a unicast message to the source device. The message contains the MAC address associated with the intended IP address. The source device learns the MAC address from the message. It saves this address in the ARP cache for further use. If it gets a data packet for the same IP address again, it uses the cache entry instead of repeating this process.